Imagine navigating a virtual reality with contact lenses or operating your smartphone underwater. This and more could soon be a reality thanks to innovative e-skins. A research team led by the Helmholtz-Zentrum Dresden-Rossendorf (HZDR) has developed an electronic skin that detects and precisely tracks magnetic fields with a single global sensor. This artificial skin is not only light, transparent and permeable, but also mimics the interactions of real skin and the brain, as the team reports in the journal Nature Communications. In recent years, the realm of bioelectronics has made enormous strides, opening new possibilities for enhancing human-machine interaction. One of the most intriguing advancements in this field is the development of magnetoreceptive electronic skin, e-skin. This cutting-edge technology integrates magnetic sensing capabilities into flexible, wearable devices designed to mimic the human skin's sensory functions. Inspired by the way some animals can perceive magnetic fields, magnetoreceptive e-skin seeks to provide humans with a new layer of sensory input, enabling an enhanced interaction with the environment. Electronic skin, e-skin, refers to a flexible, stretchable, and wearable material designed to mimic the functions of biological skin. E-skin is typically equipped with various sensors that enable it to detect stimuli such as pressure, temperature, humidity, and stretch. These sensors are typically made from conductive materials and are integrated into the e-skin structure to offer a wide range of functionalities. The primary goal of e-skin is to provide the wearer with a tactile sense of the environment. This technology has applications in prosthetics, robotics, wearable devices, and human-computer interfaces. The incorporation of sensory functions into e-skin opens up new opportunities for advancements in medical fields, robotics, and even augmented reality. Originally developed for robotics, e-skins imitate the properties of real skin. They can give robots a sense of touch or replace lost senses in humans. Some can even detect chemical substances or magnetic fields. But the technology also has its limits. Highly functional e-skins are often impractical because they rely on extensive electronics and large batteries. Previous technologies have used numerous individual sensors and transistors to localize sources of a magnetic field, similar to touch sensors in a smartphone display. Our idea was to develop a more energy-efficient system that is more akin to our soft human skin and thus better suited for humans, says Denise Makaru from the Institute of Ion Beam Physics and Materials Research at HZDR. Magnetoreception refers to the biological ability to detect magnetic fields. This phenomenon has been observed in a variety of species, including birds, fish, and even some mammals. Magnetoreception enables these animals to navigate, detect environmental changes, and orient themselves in space using Earth's magnetic field. In humans, however, magnetoreception is not a naturally occurring ability. While there is some evidence suggesting the human body can respond to magnetic fields, our capacity to perceive them is limited. This is where magnetoreceptive e-skin comes into play. By integrating magnetic sensors into electronic skin, researchers aim to give humans a new, enhanced sense, much like how echolocation provides an additional sense for certain animals. Since its inception, e-skin technology has evolved significantly. Early e-skins were designed to detect basic stimuli, such as pressure or temperature. However, with ongoing research and technological advancements, more sophisticated versions of e-skin have been developed, which can also respond to more complex stimuli like magnetic fields, light, and electrical signals. Magnetoreceptive electronic skin represents the next frontier in this field, building on the foundations of existing e-skin technology but adding the ability to sense magnetic fields. This addition has the potential to significantly enhance the functionality of e-skin by incorporating a new dimension of sensory perception. The researchers therefore replaced rigid, bulky substrates that usually host electronics with a thin, light, and flexible membrane that is just a few micrometers thick. The entire membrane is optically transparent and perforated, making the artificial skin permeable to air and moisture, allowing the real skin underneath to breathe. However, such an ultra-thin membrane can accommodate a limited amount of electronic components. This is why novel e-skins feature a magnetosensitive functional layer which acts as a global sensor surface to precisely localize the origin of magnetic signals. Since magnetic fields alter the electrical resistance of the material, a central analysis unit is able to calculate the signal location based on these changes. This not only emulates the functioning of real skin but also saves energy. Magnetoreceptive e-skin relies on the incorporation of materials and components that can interact with magnetic fields. To achieve this, magnetoresistive materials such as iron oxide nanoparticles, carbon-based materials, or even magnetic semiconductors are embedded into flexible substrates which form the e-skin. The key technology used for magnetoreception in e-skin involves the integration of magnetic sensors called magnetoresistive sensors. These sensors change their resistance in response to the presence and strength of a magnetic field. By incorporating arrays of these sensors into a flexible and stretchable material, scientists can create an e-skin that responds to changes in magnetic fields. One of the challenges in creating magnetoreceptive e-skin is ensuring that the sensors are both sensitive and durable. Researchers are focused on improving the sensitivity and flexibility of the sensors to ensure that they can accurately detect weak magnetic fields, similar to how some animals can sense magnetic fields at low intensities. Such large-area magnetosensitive smart skins are a novelty, says Pavlo Makushko, PhD student at HZDR and first author of the study. Conceptually, e-skins now work more like the human body. No matter where I touch real skin, the signal always travels through nerves to the brain, which processes the signal and registers the point of contact. Our e-skins also have a single global sensor surface, just like our skin. And one single central processing unit reconstructs the signal, just like our brain. This is made possible by tomography, a method that is also used for medical MRI or CT scans. It reconstructs the position of a signal from a large number of individual images. This technology is new for e-skins with magnetic field sensors. It was previously considered too insensitive for a low signal contrast of conventional magnetosensitive materials. The fact that we validated this method experimentally is a major technical achievement of the work, as Makushko emphasizes. The new e-skins seamlessly track signal paths, enabling applications that recognize digital patterns written by a magnetic stylus, touchless interactions in virtual reality, or operating a smartphone in extreme environments, even when diving. Often, the wearer of a magnetoreceptive artificial skin is not a human, but a machine. At the same time, magnetic field sensors are less susceptible to interferences than conventional electronics. Robotic systems could use them to detect movements, even in complex environments where other methods fail. In winter, users could operate a smartphone equipped with optically transparent magnetic sensors via a magnetic patch on the fingertip of a glove with no interference from third-party electronics. Magnetoreception does not act as a compass, but offers a unique communication channel between humans and machines. One of the most promising applications of magnetoreceptive e-skin lies in the realm of prosthetics. Currently, prosthetics are limited in their ability to provide sensory feedback to the user, often requiring separate devices to sense environmental factors. Magnetoreceptive e-skin, however, could potentially offer a means for amputees to perceive magnetic fields, improving their spatial awareness and sense of orientation. For example, a prosthetic limb equipped with magnetoreceptive e-skin could allow a user to sense the magnetic fields generated by nearby electronic devices or even detect the position of objects through changes in the magnetic field. This would greatly enhance the prosthetic's functionality and improve the user's experience. Magnetoreceptive e-skin could significantly enhance human-robot interaction, HRI. Robots equipped with e-skin sensors can better perceive their surroundings, improving their ability to navigate complex environments or even interact with humans more naturally. The ability to detect magnetic fields could enable robots to better understand their spatial relationship to nearby objects or other devices. Additionally, by integrating magnetoreceptive e-skin into wearable exoskeletons, it is possible to improve the interaction between the human body and the robotic system. This could lead to better control and feedback in assistive devices, where the user can feel more in control of their movements. The integration of magnetoreceptive e-skin with augmented reality, AR, or virtual reality, VR, systems could open up new frontiers in immersive experiences. Magnetic sensors could track a user's hand movements or other interactions with AR, VR systems, offering a tactile sense of virtual objects or environments. This could improve the overall user experience by providing more realistic and nuanced feedback. For instance, when interacting with a virtual object, a user might feel a subtle push or push-pull sensation generated by the magnetic field of the object, adding a layer of immersion to the virtual environment. Such applications could find use in fields like gaming, training simulations, or even medical rehabilitation. While magnetoreceptive e-skin holds significant promise, challenges remain in terms of sensitivity and accuracy. The human body itself can generate weak magnetic fields, and e-skin must be sensitive enough to detect subtle changes in the environment while ignoring internal sources of interference. Researchers are working on improving the resolution of magnetoresistive sensors to ensure that they can detect a wide range of magnetic field strengths, from those generated by the Earth's magnetic field to stronger, man-made fields. Durability is another challenge for e-skin technology. The materials used to create magnetoreceptive e-skin must be able to withstand the wear and tear of daily use while remaining flexible enough to conform to the skin's surface. Stretchable electronics are prone to failure when subjected to extreme deformation, and ensuring long-term stability without compromising performance is a key area of research. Another challenge is the power consumption of e-skin. Advanced sensors and processing units integrated into the e-skin may require substantial energy to function. Developing low-power, energy-efficient solutions is critical for the widespread use of magnetoreceptive e-skin, particularly for wearable and prosthetic applications. The future of magnetoreceptive e-skin is exciting, with the potential for groundbreaking applications across various fields. As research progresses, we can expect to see improvements in sensor sensitivity, durability, and energy efficiency. New materials, such as flexible graphene-based electronics or organic semiconductors, may offer enhanced performance and lower production costs, making e-skin more accessible and practical for a wider range of applications. In the long term, the integration of magnetoreceptive e-skin with other sensory technologies, such as visual, auditory, and haptic feedback systems, could revolutionize the way humans interact with technology. It may enable new forms of sensory augmentation, where users can experience enhanced perception of the world around them, providing richer and more intuitive interfaces. Magnetoreceptive electronic skin represents a transformative leap in wearable technology, combining the sensory capabilities of biological systems with the flexibility and adaptability of modern electronics. With applications ranging from prosthetics and robotics to augmented reality, magnetoreceptive e-skin has the potential to enhance human-machine interaction in profound ways. However, significant challenges remain in improving the sensitivity, durability, and energy efficiency of magnetoreceptive e-skin. Ongoing research and innovation in materials science, sensor technology, and fabrication techniques will be crucial in overcoming these hurdles. As the technology matures, magnetoreceptive e-skin could become a fundamental component of next-generation wearable devices, unlocking new possibilities in fields as diverse as healthcare, robotics, and immersive media. This outline provides a structured and comprehensive overview of magnetoreceptive electronic skin, including its science, applications, challenges, and future directions. You can adjust the depth of each section as needed for your specific requirements.